So welcome to our Spike and ECoG workshop here at SfN. My name is Christoph Huber, and here's a short timetable of the workshop today. So it lasts from 6:30 to 9:30. And I will start with an example of spike analysis, the real-time position reconstruction of hippocampal clay cells. Then Mel Williste, already coming in, will talk about prosthetic arm control with monkey experiments. Then we have Robert Goodman talking about the analysis of spikes in the cerebellum. Then I will talk about the EEG and ECG mapping in rat experiments. And finally, Kai Miller, who is coming a little bit later on, talks about ECoG experiments that he's doing at his university. So Kai Miller is from the University of Washington, and he's one of the pioneers in ECoG recordings, and has done a lot of very nice real-time studies in this field. Then we have Mel Williste from the Motor Lab from the University of Pittsburgh. He's working on different neural prosthetic devices, and he's also the author of this famous paper where the monkey was controlling a prosthetic limb in a closed-loop experiment. So we are very happy to have you here, and looking forward to your talk. I'm coming from Google Technologies in Graz and g.tec Medical Engineering, that's located in the north of Austria. So Google Technologies is producing the hardware and software components and is involved in several research projects. And g.tec Medical Engineering is doing the sales. So be careful if you need something from g.tec, they want to sell you something. And Austria is between Germany and Italy. So we don't have kangaroos, as some people think. But we have Wolfgang Amadeus Mozart, you might know this guy. We have some castles in Vienna. And in Graz we have a clock tower. And some 100 years ago it was also surrounded by a nice castle. But Napoleon Bonaparte destroyed this castle, so now we have only the clock tower left. So is there anybody from France here? I just wanted to say thank you for that. And I have him now, Arnold Schwarzenegger here. So he was born in Graz. And yeah. So g.tec is designing hardware and software components for biosignal research. And the technology is used for EEG recordings, but also for invasive recordings, ECoG. You can do heart activity measurements, muscle activity, eye movement, and so on. And the devices are based on a rapid prototyping environment with MATLAB and Simulink, which allows you to modify the signal analysis quite easily and fast. We are a private company. We have biomedical engineers, informatic engineers, also psychologists. And our main customers are universities, research centers, industry, and university hospitals. And we are the first producer of plain computer interface devices. You can just buy a BCI system and start your research. We sell it currently in more than 60 countries. The most important markets are, of course, the US, Europe, and Southeast Asia. And we have also a very good customer here from the Wadsworth Center, Theresa Morn, and yeah, also other people. Here are some research projects where we are involved from the European Commission. So the first one is the synthetic chip project. It will also be introduced today, so I skip it. Then in Smart Homes for All, we are coupling BCI systems to real smart homes so that you are able to control your TV set, to switch on the light and so on. We are also working on a rehabilitation gaming system, which is used from stroke patients to have a faster rehabilitation. In Brainable, we are combining BCI systems with virtual reality system and social environments, such as Second Life. And in Decoder, we use plain computer interface technology for coma patients to identify if the coma patients are still able to communicate. And there are always some cases which can still use a BCI system, but you wouldn't notice that this coma patient can do something. In Better, we combine BCI technology with exoskeletons, again for stroke patients, for faster rehabilitation, and in Verre, we try to control avatars. So it's quite funny because this Verre project was submitted when the movie Avatar came out, and it started when Avatar got the Oscar. So I hope it's a good sign of our project. And the last one is Alias, where we combine robotic devices with PCI systems. So we got also several awards for the technology. The first time we were thinking must be a mistake. But this year we got, for example, the Microsoft Innovation Award for the PCI system. So it should be quite okay. Here are some cooperation partners with Mel Slater from University of Barcelona. We worked now together for almost 10 years. He's one of the pioneers in virtual reality systems, and he built the first cave system in Europe. With ECoG, Mavi Sanchez, she should also come. We do spike recordings in rats, mostly place cells. Then with the University of College London, with Anthony Steed, we work also on virtual reality. We work, of course, with the University of Technology in Graz, Gerd Fritschler's lab, who invented more or less the event-related desynchronization for motor imaginations. Then we have Gavin Schalk, Eric Sellers in the Wadsworth Center. Eric actually moved to Tennessee now. And we have Matti Mintz for recordings in the cerebellum. So the first lecture is about basics for spike and ECoG recordings and analysis. So basically a BCI system needs a patient, a subject, or some animals, monkeys, rats. We are extracting the different brain signals, and the BCI system generates a control signal in order to control another device or to give feedback in form from cursor movement. And in this case, it's important that we are just using brain activity and not other functions of the body like EMG activity, ECG, whatever. This would be a human-computer interface. So the University of Michigan, Simon Levin, for example, called such a system direct brain interface because he implanted the electrodes directly onto the cortex as first person who used human subjects for BCI control with ECoG. So there are different applications for BCI systems. The most important and useful one is probably the spelling device, which can be used by logged-in patients to select characters and words to communicate. You can use it for prosthetic limb control, which is also useful for stroke patients to increase the speed of rehabilitation. Nokia, one of our customers, is using BCI systems, for example, to control mobile phones. You can use it for gaming. In this case, we have a simple ping pong game that everybody knows. Nowadays, many art installations are coming up, so they use it for composing music and so on. Japanese people like to use BCI systems for robotic control, of course, and for virtual reality control. So what do you need? Again, the subject, patient, or animal. You connect it with a biosignal amplifier to a real-time processing system. So we usually use MATLAB and Simulink because this allows you to use all the toolboxes for MATLAB. And then you can also add your own real-time analysis algorithms. And you need something like a stimulation unit which gives feedback to the subject so that you can learn in a closed-loop experiment to perform the task. So in BCI development, there are several steps. First, you can, for example, select parameter estimation and classification algorithms. Then you have to implement the algorithms. You do some offline simulations with some data that you already have acquired. And then you have to connect it to the real world. This means you have to connect the biosignal amplifier. You generate your real-time code and you do your real-time tests. So on the left-hand side, we have the traditional approach, and you have several iterations between the algorithm development and the hard and software design until you reach your final system for your experiment. And with a rapid prototyping system, the algorithm design and the prototyping is done in one step, and this allows you to do your experimental setup much faster. So if you look at the effort for the traditional approach, you see it takes longer, you need more money, more time to realize your experiment, and with rapid prototyping you can do it much faster. There are 4 different concepts for realizing a BCI system. So the oldest one are the slow cortical potentials. They were firstly used by Niels Bierbaumer from Tübingen. And basically with some biofeedback strategy, you learn to control the cursor movement on the screen. The next principle are steady state evoked potentials. So you can, for example, have a flickering light that is flickering with 10 Hz. And if you're looking at this slide, you will see the same frequency in the EEG spectrum, and you can analyze it. Then you can use the event-related non-phase log changes of oscillations. So this is mostly motor imagination. If you think about your left or right hand, you can change the amplitude of the alpha and beta rhythms. And the last principle are the evoked potentials, where you can use, for example, a P3 evoked potential for spelling. But we also know that place cells exist. Place cells were discovered in 1971 by O'Keefe, and basically these neurons start to fire if a rat is in a certain position in an environment. There are also other cells, like grid cells, which show a triangular pattern if the animal is moving around in space. There are also head direction cells. So if you're looking into a certain direction, specific cells start to fire, and they are independent from position, so it doesn't matter where you are located. So if we look at the brain of a rat, for example, we see in the middle the hippocampus. It's formed like a C, and on top of it we find the place cells, on the bottom we find the grid cells, and here we find the head direction cells. Here's an image of a typical firing field of the place cells in the CA1 region. So a red color means that the neuron has its maximum firing frequency exactly at this single spot, and blue means the neuron is silent at all the other positions. And on the right hand side there's a grid cell, and you see this typical triangular shape of grid cells. They were discovered a little bit later on than the place cells. So for recording single cell activity, you need a needle electrode that you place directly beside the cells, so you have to stick the electrode into the brain. And of course the needle must be very thin. It must be similar to the neuron dimension. And I have one here. As you see, it's so small that I don't see it. So this is a tetrode in a stainless steel tube. There are 4 wires included that pick up the activity of the single cells. I can pass it around so that you can see it a little bit easier. And because the wires are so small, the impedance is very high. And therefore you need a head station amplifier, which is very close to the electrode, and the main amplifier, which is suppressing the noise and giving you the typical shapes of the spikes like indicated here. And of course different neurons give you different shapes of the spikes. So the next goal is to find out which neuron produced which spike. That's called spike sorting. So if we look at the action potentials, action potentials are the electrical signals that carry information over long distances within your body, and they are produced by changes of the permeability of the membranes. And you need a biosignal amplifier to measure these small spikes, because they have only an amplitude of about 50 to 100 microvolts. And they are also quite sharp and short-lasting. So normally you have to sample between 10 and 50 kilohertz to be able to pick it up. If you sample with 256 hertz, you're just missing that.